If you haven't heard of the three-body problem, either from the book/TV series or just in general, it's essentially an unsolvable physics problem which states that there's no general solution to predicting the movement of any set of three orbiting bodies over time. In the three-body problem, there are two basic categories: closed or periodic orbits and open orbits. Closed orbits are orbits where bodies generally repeat their paths and remain in a consistent orbit, while open orbits end with one or more of the bodies being slingshot off into infinity. With these definitions in place, let's try to make simulating this infamous physics problem a reality. Obviously, the first thing we're going to need are some bodies to apply gravity to. I don't mean to brag, but I'm pretty good at 3D modeling. Oh yeah, Unity already has spheres. Well, let's get a few of these in place, add a gravity script with starting velocities, and see what happens. Maybe the gravity needs to be a bit higher. Alright, there's some orbiting happening, kinda. Clearly I just need to tweak my values a bit. This one doesn't quite work, neither does this. I'm noticing a pattern. Are you trying to tell me that I can't just plop down three bodies at arbitrary distances, thoughtlessly apply random velocities, and get a cool result? This was unexpected. Let's try to take some kind of methodical approach. Okay, sounds like the key is to use an equilateral triangle. Well, that still didn't work. Let's tweak a little more. Well, this one is kind of doing something, but it's still running off into the sunset, which is not ideal. I decided to do a bit more reading and found that apparently the most stable orbit is the figure 8 orbit, so maybe I should go for that before trying chaotic orbits. It sounds like it's best to have them all start in a straight line, so behold, the most stable orbit. Seems like it still needs some work. I started by switching over to something called Verlet integration for the gravity calculations, because apparently it's more accurate, and I added a system to record time and reset the bodies if they get too distant from one another. Let's try again with some adjusted velocities. Well, the reset works, but this really isn't coming together. After some thinking over and more reading, I decided to start with a simpler system called the restricted three-body problem. It still involves three bodies, but two of them are functionally immobile, and the mobile body has an infinitesimal mass. Apparently, this setup has application for exploring the orbits of satellites and other small bodies around planets, because the mass of the satellite is so small it can basically be ignored. Here's how it looks. I made two of the bodies larger for visual clarity, and the third body is the massless particle that will be moving around. Alright, this isn't the most exciting thing ever, but at least it appears to have a stable motion. Let's add in a little x velocity. Okay, maybe with slightly changed values. Oh, we're actually getting a figure 8. It's not totally consistent, but at least it looks like a closed orbit. We can see over an extended period it seems to oscillate, but it doesn't go flying off to infinity. From here, I managed to find another closed orbit after adjusting some values. Alright, at least closed orbits are possible if we isolate a few variables. This gave me the confidence I needed to get back into the true three-body problem. I mentioned that I added a failure reset if the bodies got too distant, and now I made it so that the gravity value would be slightly randomized each time a system failed. I then added a timer to record how long a given attempt lasted at a certain gravity value and let it run for a while. I also manually adjusted some values along the way. Eventually, this happened. It looked pretty promising. I added in some lines and set the camera to follow it to see what would happen. So it's definitely a wandering orbit, but it seems to generally stay within a certain range. At this point, it's lasting quite a while. I've decided to call it the third wheel, because purple and green seem to have a lot of fun, and then red is just kinda swooping in every once in a while. I think this might go on forever. Wait, red got kinda close there. Okay, yeah, it's getting way too close. Well, I guess that's why the third wheel should keep its distance. I feel kind of silly because it was at this point that I realized that of course a chaotic bound orbit is a contradiction and can't be assumed to last. The whole premise of the three-body problem is its unpredictability. So it's basically inevitable that for chaotic orbits, at some point a body will be slingshot off into infinity. I think at this point, I'm ready to give periodic orbits another try. But this manual adjustment is getting kind of tedious, and I'm too dumb to mathematically deduce the correct values. If only there were some way to speed things up. That'll do. I set it up so that if a system lasts more than 60 seconds, I would get notified, and this gave a lot of results for chaotic orbits that would last more than a minute. But if I'm going to get something stable, I'll have to find the correct initial conditions. So I found some new potential values for the figure 8 orbit online from the Stack Exchange post, and I think with the new system in place, we'll be able to make some progress. I manually set positions and velocities and let the gravity values get randomized on failure. I really wanted to be sure I had something stable, so I set the minimum candidate threshold to 300 seconds, and all I had to do was wait. There, we got one. It's showing a gravity value of around 1.7, and after a little while longer, a lot more results started rolling in. They all seem to have a gravity value above 1.6, so it's good that there's at least a consistent trend. Here's what a candidate looks like with line trace. It's definitely not perfect and not periodic, but it seems to be a step in the right direction. I then limited the range of the gravity to roughly 1.7 and added a system which recorded coordinates that a body traversed and checked if it would travel across those same points again. If a body touched all the same points twice, then this would show periodicity. Some of the orbits would get a single stray match here or there, but nothing perfectly aligned. After enough messing around, I found that the gravity level was still too low, and 1.9 gave much more consistent results. The test still didn't turn up any perfect matches, so I decided to give visual testing another try. And wow, just look at these. Some of the gravity values between 1.9 and 2 really gave some compelling results. The one on the left here looks almost perfect. Here's another good result. I really wanted a perfect orbit, so I spent a few more hours trying to fine-tune it as much as I could. In the end, I still didn't get any perfect matches within a coordinate tolerance of 0.001 from my system. And at this point I started to question my conception of a periodic orbit. What did it mean that the figure 8 orbit is supposed to be the most stable of the periodic orbits? Do the other orbits decay? I did some more digging, and it seems that I was yet again operating under a misconception. While there are theoretical perfect conditions for some periodic orbits in the three-body problem, it seems that even in simulations, orbits that are labeled as periodic still often decay. Even for the figure 8, I'm still unsure if it's possible to actually prove that a specific simulation could last indefinitely or not. Settling on this conclusion, I decided to choose one of the visual samples that looked the closest and move on to other periodic orbits. I ended up finding a paper about these, BHH orbits, and they included some diagrams and tables for really cool looking periodic orbits that use bodies with different masses. I took the values for the first sample and got to work. I followed a similar methodology to before, where I looked for the most stable orbits based on duration for a randomized gravity value, examined the resulting visual orbits, did some fine-tuning, and selected the closest match of the bunch. This actually worked super well, and now we have a second periodic orbit. You might have noticed that this formation creates these slightly offset lines, and that's because there is a rotational value for each BHH orbit, where it rotates that many degrees per orbital cycle. The images you see in these diagrams are normalized by placing them in a rotating frame of reference to counter the orbital rotation, but in the result here, you can see the rotation in action. I'm most interested in the second orbit pattern because I think it looks the coolest, so let's give it a try. We'll just plug in the values and... wow, I guess I should have expected that the same gravitational value would be successful because it's from the same paper, but it still surprised me nonetheless. This one has a much smaller rotational value, so there are only these slight offsets each period, which makes a really cool pattern. At this point, we've been able to recreate 3 periodic orbits. There are a few more periodic orbits for bodies with equal mass that I want to try, and now that I've had some success and know what to expect, I think it will be pretty quick. I first want to go for the circular orbit, and it seems like all I need to do is make an equilateral triangle and then add velocities that are tangents to a circle circumscribed around that triangle. Okay, we've already got some vaguely circular orbits, that's a good sign. This one looks pretty good. There are a few decent orbits here, but wait. Is that another periodic orbit? That's pretty crazy. It looks like different gravity values can give another periodic orbit for these initial conditions. I wasn't expecting that. So we've managed to add 2 more periodic orbits to our list, but they're not very stable. Overall, I'm pretty satisfied with the results so far, but I can't help but want something that's truly stable. I have an idea that breaks the convention of the 3-body problem and doesn't at all reflect reality, but I think it will be fun. What if the masses of the planets change depending on their distance from one another? Well, let's see it happen. This is certainly a pattern we haven't seen before. How about for random starting conditions? Okay, so it doesn't provide the universal stability I was looking for. And even in the case of periodic orbits that aren't stable, it still manages to fail. Maybe some of these configurations could create a perpetual orbit, but I'm not willing to sit around for an eternity to find out. Alright, the last thing I want to do is try to find some periodic orbits that I haven't seen already online. After the first few hours of this project, I began to doubt if this would be possible, but I think with the BHH paper, it should be doable. They describe all the initial conditions for BHH orbits. I think as long as I choose random masses and positions that meet these criteria, and then make a calculator to ensure the net momentum of the system is 0, we should be able to get some results. I first did a sample test with 2,000 simulations, and I almost immediately got 39 potential candidates, which was a great sign. These candidates have a much higher chance of being periodic compared to any test before this due to the initial conditions and boundaries we've set. Let's now try visual testing. Almost immediately from a test pool of 300, I can already see some orbits that look fairly periodic. This one's pretty cool. It reminds me of a sunflower. I reset the samples a few times and consistently found numerous periodic orbits each time, and then I stumbled on what might be the most interesting orbit so far. Here it is in isolation. If you find yourself wanting to stare at these orbits for even longer, I have good news. You can access this simulation for free with the link in the description, and it can all be used within your browser. There's even a testing mode with optional BHH restrictions where you might find some cool patterns not shown in this video. Thank you for watching. Until next time.